Hi friends, this is PH3503L Laboratory Experiments by Dr. M.R. Gadhvi. Zener Diode characteristic and the load regulation. Download the lab manual. Read the experiment before this virtual lab sessions. I request thoroughly that as you are doing a virtual lab sessions, please read the experiment thoroughly, then only you can understand the experiment in a better fashion. Try to understand the behavior of a Zener experiment, looking through the observation table and the data, especially when you are drawing the curves or the graph. The mechanism of a Zener diode. The story begins with the honored scientist Clarence Melvin Zener, who was an American physicist and doing a research on breakdown effect in a rather electrical breakdown effect in the insulator. Later on, the Bell laboratories are finding the same behavior in the semiconductor, especially in the reverse bias. Just to honor the mechanism, just to honor the scientist, the same mechanism has given the name Zener breakdown effect, and the device is also called as a Zener diode or a Zener diode. How exactly it works? When you are applying a high reverse bias voltage to a PN junction, then basically you are applying a high strength electrical field across the depletion layer or a junction. Because of a high junction potential, you are basically allow the electron tunneling through the depletion, and therefore numerous charges will enhance in the conduction band. Because of a sudden increment of a conduction band carrier, you are finding a sharp increases in the reverse bias current, and this is phenomena is known as a Zener effect, especially observed in the Zener diode reverse bias region. The Zener diode looks like a brownish red on an average, and the symbol of Zener diode is almost similar to the conventional diode. In case of a conventional diode, this line is a straight one. In case of a Zener, the tip of that straight line, which is representing cathode, is little bit tilted. If you look at the device Zener, where you are finding a black ring on the device, which is also shown cathode. The flow of a current is you are finding from anode to cathode. The very interesting thing, you have heard the avalanche breakdown effect in a normal diode, and the Zener breakdown, it is a speciality of a Zener diode itself. But in case of a Zener diode, you are having the chances of both the Zener breakdown as well as the avalanche breakdown. How and when they occurred, so I have make a tabulated form and you will get the flavor of it. Point number 1, in case of a Zener breakdown, on an average it is observed that Zener diode having the Zener voltage, and therefore the breakdown will be observed in between the range of 5 to 8 volt. The range of 5 to 8 volt of a Zener voltage is given because the dopant will be different in each and every batch of a Zener diode, and therefore there is a range of a 5 to 8 volt. How it is occurred? When the valence electrons are pulled into the conduction band due to the high electrical field applied across the junction depletion region, and therefore the carrier will be tunneled through the depletion region and conduction population will be enhanced. This will lead a sharp increment Zener current or the reverse bias current. So if I draw the IV characteristic or VI characteristic of a Zener diode in a reverse bias region, where I will finding out the breakdown or the sharp increment of a reverse bias current, that is very sharp. In context to the avalanche breakdown, in case of a Zener diode, you can observe which is greater than the 8 volt. That means once the Zener diode breakdown will be getting over, if you still increases the reverse bias voltage, then you have a chance of a avalanche breakdown. What exactly the avalanche breakdown? First of all, one should remember that in case of a avalanche breakdown, minority charge carrier become the dominating. The minority charge carrier become highly accelerated by the high potential field, and therefore they are sufficiently energized and they are colliding to the many other carriers, and therefore their kinetic energy is sufficient to imparted, and therefore they are able to pull out the electrons from the covalent bonds, and there that is the mechanism is occurred which increase the population of the electron in the conduction band. So the valence electrons are pushed into the conduction band due to the energy imparted by the colliding accelerated minority charge carriers, and therefore the avalanche will be increased. As there is a minority charge carrier are taking part into this, that means the increment of this current will be not sharp as you have observed in case of a Zener breakdown. So here you are finding out in the IV characteristic the avalanche breakdown increases gradually. If you compare over here, it is increases sharply. You can look at in the characteristic curve very nicely that forward bias region of a Zener diode and the conventional diode is identical. If I will eliminate this line, that is a Zener breakdown, then this is the pure characteristic of the reverse bias or the conventional bias, conventional diode, where the current will be amount of the microampere. But this is a Zener diode where the anode is highly dopant, and therefore you are getting the reverse current is in the order of a milliampere. When you are applying a reverse bias voltage up to a certain voltage, let us say up to this point, then that would be a Zener breakdown will be triggered, and a more number of electron will be tunneled through the depletion, and sudden of a conduction electron will be enhanced, and therefore a sharp increment of a Zener current or the reverse bias current, and that is what a Zener breakdown. If you still increasing the reverse bias voltage, then the slowly minority charge carrier getting accelerated, and that is allow to get imparted the energy to enhance the population of electron in the conduction band, and therefore this is mechanism is little bit gradual, and therefore you are not finding a sharp increment but a slowly incrementing of the reverse bias current, and that is avalanche effect in case of a reverse bias Zener diode characteristic. Okay, the similar curve are also shown here, so just check it up here. That forward bias we are not doing a characteristic study in this syllabus, so we are just focusing on the reverse bias. How to measure the reverse bias breakdown voltage? Then one has to draw a tangent from your data point and make a tangent where you are intersect the x-axis, that is your Zener breakdown voltage Vz. Okay, so that way you have to get it the exact Vz from your graphical representation. The next one is the circuit.
So today's experiment is the Zener diode as a voltage regulator.
The circuit is also in the PowerPoint presentation is given, but this is the presentation circuit. This is one of your old student or ex-students journal, and generally we are writing on right hand side aim, apparatus and explanation. So let us try to connect the circuit. The voltmeter should be connected at a V out, so positive and negative. Voltmeter we will be set on a V, one of the terminal, the positive terminal on the V, and the ground as a common. The pointer we will be kept on some around 20 volt, because input battery is some around at a 12 voltage. So let us connect this one, the black with the ground and the red as a V out. Secondly, we need to measure the IZ, or you can say the Zener current, or the current which is passing through the Zener diode. So this meter we will be considering as a current meter, and the pointer we will kept at a 200 milliampere, because sometimes Zener is passing a value of some current more than 50 milliamps and so on, and therefore I do have only option. One is 20 milliampere, another is a 200, so I kept on a 200 milliampere. One chosen terminal is a milliampere, the second one is as a common terminal. So let's connect at a place of a IZ, and so one will be at here, the second one will be at the IZ negative. We do have the Zener diode is here, and we have two options. Okay, for just to know how each and every Zener diode responding differently, so the board has given with the facility with the two diodes. Okay, so we will be selecting a diode, so I will kept as a one cathode of the red line of this one. The tilted line is of a cathode of a Zener, so I am selecting orange one, so I will kept it here, and another, that is anode of the Zener, is considered to be the another terminal, so orange. So this is your connection of your circuit. One more resistance in the path over here, in the path of the Zener is there, and it is a current limiting resistor, so that also we will be connecting. So one of the connection in a series, so like this, the second one will be like this. So this is your complete circuit of part 1, that is the characteristic of a Zener diode. What we will do, we will change the input. We will change the input, and we will measure the output, or you can say Zener voltage, and the current which is passing through the Zener, that is IZ. We are not interested to measure the V in. Okay, we are in, because in your assignment, the graph you have to draw, that is IZ versus VZ, and therefore I will be measuring the two parameters: the current passing through the Zener, that is IZ, the voltage across the Zener, that is a V out or the VZ. So in this video clip we have learned how exactly the circuit connection will be taken place. The next video clip is for how exactly the part 1, that is the characteristic curve of a Zener diode, can be executed. Okay, so let us start the experiment. Then if I will be increasing the input voltage, right, you can check it up over here. If I will shift this meter to input voltage, I can see a certain volt value in the okay, board is, let me on the board. So now board is on. So if I will increase this one, the potential over here is changing. Okay, and The characteristic of a Zener diode, as you have seen in your PowerPoint presentation, that is the I you are taking on the y-axis and the Z you are taking on the x-axis, and Zener is always connected in a reverse bias mode, and therefore your current is also negative, your voltage is also negative, and therefore your graph will be fall into the third quadrant. Am I correct? So now if the input voltage is you are connecting, right, and you are giving a certain the voltage what you have given here, the same voltage you can measure it as an output voltage, but current is still zero. That means the Zener is not yet triggered, it is still in the cutoff mode. Now when you have to increase the voltage till you are notice a very first pulse of a current which is passing through the Zener, that is a IZ. If I am not wrong, the present Zener diode is some around at a 4.5. So as you approaching 4.7, a very little current is you can observe over here. And now what you have to do, you have to note the current for what the entire range the current is showing you a 0. Then you have to increase a certain value of output voltage, right, and current is increasing. What we are observing, the increment value of a voltage across the Zener is growing slowly, but the current increasing very abruptly. You can see from 0.12 it's 2.8, so it is almost 30 times higher, whereas the voltage is just changed from a 5 to 6.9, so it's roughly 2 voltage. So this is how you can visualize the Zener is working as a voltage regulator. That means you have a freedom to increase the value of a current, but voltage is remain almost stagnant. You can notice here 5 to 7, so hardly it is increased by 20%, right? So in this clip we have seen the Zener characteristic, how exactly the data will be taken for the Zener characteristic. The next video clip is for how exactly the load regulation will be executed. Let us see the next clip. So now this is the second part of the experiment where we are looking for the Zener as a load regulator. So we will be in a plan to connect any particular load in connection to the Zener. So now this is which is not active part of your first setup of your experiment. Now we will be take this last part of your circuit as a part of your experiment. So in the case of a load regulation, what we will do, let us see how to do the connection. So now I am interested to measure the current IL rather the IZ, because now the load current to be underlined, because I am want to check the characteristic of a Zener as a load characteristic. So I need to connect the load. For a load, one port meter is connected from inside. You can see a variable resistor symbol is there, and the variable button is given here. So as I am changing this one, okay, the load will be changing in between these two terminals. So what I will do, I will connect one terminal from here to here, so the load will be part of the circuit, but I think it is already part of circuit, so no need to connection between here to here and here to here. But now instead of IZ, now I will measure the IL. So I will replace this IZ meter at the place of a IL, because you have already taken the data of a IZ, but the IZ should not be kept open, because the current meter is in general connected in a series. So if this is
going to be not shorted, the circuit will be break. So to avoid the discrepancy, either I should connect a current meter over here, and if I don't have a current meter, I should connect a one jumper from a positive to negative. So let me connect a one jumper from this to this. By connecting this jumper, you are proving that now circuit is again stable. Now in a load regulation, there is a one condition. Your input voltage, that is V in, should be, your V in should be greater than Vz, or the Zener voltage. That means Vi should be greater than Vz. Vi should be greater than Vz. Let me put it the condition on the journal, and let me show you. This is a condition, so it should be greater than that. Then only your circuit will be working nicely. So first of all, I will check the input voltage. So by removing the upper terminal, removing the upper positive terminal of the V out, I will put it at a V in, and I will switch on the board and set the input voltage such that, so it should be greater than. Now if you remember and look at your first table, the Vz is some around at a 4.7 or 4.8. I will keep this meter is more than 5.5 or a 6 volt. So I am sufficiently high compared to the Vz. Let me put it on a 6.5, and then I will again come to the Vz. While you are changing a meter or anything, the circuitry board should be off. So I am making off, and now I am changing the meter. Okay, so now my duty is to measure the load. So now my input is fixed, so corresponding my output is also fixed, but now I need to change the load. When load is going to be increased, naturally passing amount of the current should be less. When load is decreased, the passing of amount of the current should be changed. So to visualize a correct load regulation, you need to set a value of a V out continuously. So now switch on the board and vary the load value and correspondence V out and IL to be noted out. This is a minimum value of a current load. This is a minimum value of a load, so I have a maximum value of a current. If I will increase the button of R maximum, the current will be minimum. If I am looking the range, it start in between 5.8 to 41. So if I will scale up, it's roughly 35 milliampere in my hand. So with the interval of a 5 milliamperes, I will start with the minimum to maximum and corresponding Vz or a Zener voltage to be measured. As for example, 5.7, I have a 6.0 Vz. If I will keep it, I will make an increment of a roughly, let us say 4 milliampere. So 5.8 I will consider as a 6, 6.2 I will make it 4, so that is 10 milliampere. So roughly 10 milliamperes I am going to set. This is a 10 milliampere, and for a 10 milliampere, what is the corresponding value of a voltage, that I will note it out, and so on. I will take some around 5 to 7 data. You can also decrease the interval, like instead of a 4 milliampere you can make it a 3 milliamperes. As you have a smaller interval of a load current, you have a better resolution of the curve. Thank you.
Okay, so this is a load characteristic for the Zener. Now I will show you the last year journal pages, so you will get more clear vision for that. Now this is a third quadrant region, that is a reverse characteristic, where on the y-axis I am taking the Zener current and on the x-axis I am taking the reverse bias Zener voltage. And if you look at here, the Zener voltage is increases, but still the Zener diode is not triggered, and therefore it shows the zero current. And that's why the axis line is running parallel, or the data line is running parallel to the axis line. At some around 5 voltage, the very first current pulse is shown, some around 0.1 milliampere, and that is, you can say that the diode get triggered and start working. And after from 5 to 6, after this particular potential, the increment of Iz is tremendous, very abruptly high, and gives us the very good amount of a current, more than 12 milliampere. If you look at here, from this 0.1 to 12 milliampere, it's a huge variation, and that is because of the sudden of increment of electron or a charge carrier in a conduction band. That is what a Zener breakdown effect. Now the next part, that is the load regulation. In case of a load regulation, let me bring it to your point. This is by mistake wrongly interpreted. This is V out or Vz, and this must be the Iz, other IL, the current which is passing through the load current. And this is, you need to check it out, the IL is changing from 4 milliampere to 19 milliampere, and corresponding voltage output is changing from 4.65 to the 3. But within this, if you look at the very first 10 data or 11 in 8 to 9 data, then it is remain till 4 o'clock, 4 voltage. So 4.6 to 4 voltage is remain, you can say that just variation of 10%. That means this region of a current consumption, the Zener diode is regulating the voltage. That means your this current range, that is from a 4.65 voltage at a 4 milliampere to 4 voltage at the corresponding some around 10 milliampere. This range of a current or the load current is the very stable range of your voltage. That means within this range of a current, our present Zener diode can work as a voltage regulator. That means it can regulate the voltage. The voltage will remain constant. So this is how you have to learn exactly. At the end of the video of this session, I will be attaching a one more Zener diode as a regulator. Please look at that YouTube video link, and that is of some around of a 25-minute video link. It would be also give you a more enlightened about the topic. So thank you so much for the paying attention. Stay home, stay safe.